So my name is Sophie Choe, and I'm the founder of qAIntum.ai. We are a quantum large language model company. And unfortunately, we are not going to get into quantum large language model today. So that's going to be maybe, 4 or 5 lectures down the line. Today, we're going to talk about quantum internet infrastructure. So agenda is I'm going to talk about quantum communications, quantum computing, quantum memory, quantum transducers, quantum sensing, and then conclusion and Q&A. So the concept of quantum interconnects came from National Science Foundation and Department of Energy since 2019. So the quantum computing research community, it's been around for 40 years by now, since 1980s. So it's a well-established domain. And all the researchers by now, they know that quantum computers are not going to replace classical computers, but they're going to be good at solving specific problems. What are those specific problems? We don't know yet, but they're working hard to find them out. But the idea of quantum internet, once we figure out what those problems are and actually how to solve them, then we're going to have classical quantum hybrid internet using the existing communications computing infrastructure. And that's what I'm going to talk about. And this idea was, again, from the scientists from National Science Foundation. So the components of quantum interconnects. So the interconnects are the ones who make up this communication channel to build quantum internet. And they're composed of these components that I mentioned about. Quantum communications, we know, quantum computers, we know. Quantum memory is going to be really important for quantum computers as well as quantum communications. And transducers are devices to convert signals for when you have two different devices sharing information together. And quantum sensors are like edge devices for sensing. So this is a diagram of quantum internet infrastructure composed of satellite network, wide area network, metropolitan area network, and local area network. So based on the distance of two devices where the information has to travel, the farther they are, the more they're going to need extra devices to maintain the integrity of the information that's being transferred. So they're going to use repeaters. But this is kind of like a diagram of how the network is going to be composed of based on the Department of Energy, Office of Science, National Quantum Information Science research centers. So when we talk about using the existing infrastructure and then on top of that, building quantum information, we have to look at what do we have today. And this is the diagram of submarine fiber optics network that we use for communications. And for today's like physical communications, about 98% of that is based on fiber optics. So then you have to think the information carriers in these cables are actually photons. And then the idea that National Science Foundation and DOE has is to divide the same cable with wavelength division into quantum information and classical information, but kind of share the same channel for both types of information. So then that was quantum communication. So while researchers are working really hard to bring that about, what about quantum computing? What does that mean? So when we look at classical computing that we are using today, we are using digital computing. What does that mean? That's digits, zeros and ones. So any classical bit is in a state of 0 or 1, but not both. So when you want to compute something with 0 and 1, what you have to do is you have to do 0 first and then 1. But you can't do both of them simultaneously. But that is different in the quantum world where you heard about Schrodinger's cat. So the cat being dead and alive at the same time is the concept that we are using for computing, and that's called superposition. So let's say with a qubit-based model, when we have quantum bit, yeah, sorry, those alpha and beta, they're complex numbers. So figure with 0 and 1, just think about that as dead and alive. So complex coefficient times cat being dead plus complex coefficient times cat being alive, they coexist simultaneously. And on that state, you're applying some kind of computation. So that's inherent parallelism until you extract the resulting information for a classical use from our end. So that idea of superposition, like having both of them existing simultaneously, that's the concept superposition. And the superposition is at the core of quantum computing that we use that inherent parallelism. So that's how we are thinking that's, the idea of quantum advantage of getting computation so much quicker. In the continuous variable model, they use quantum mode. So the basis states do not stay at just 0 and 1s, but now it goes to infinity, like a system of quantum optics. When you have to express that state, complex coefficients times 0 plus complex coefficient times 1. That's kind of like in quantum optics, the probability of observing no photon in the system plus complex coefficient times 1 photon in the system and into infinity. So that's the concept. So what I'm saying is, and what quantum AI is pursuing, is that by having this higher number of basis states, you can encode much more information at once compactified because you're in a higher dimensional space. So how do we, so that's like, that was mathematics of quantum mechanics that we are using for information processing. How do we physically implement devices where those quantum mechanical mathematical rules are applied? So today, the methods with which they are being explored are superconducting, trapped ions, quantum dots, neutral atoms, and photonics. Just right here in Palo Alto, we have PsiQuantum. And about 2 years ago, they raised $450 million to deliver stable photonic quantum computers maybe 6 years from then. So I ran into them the other day. They have about 250 engineers and what have you, but they're working with elementary particles. The difficulty in all these models is that we are trying to manipulate individual particles, and nature is not binary. So the energy levels of these elementary particles come from the ground state and one higher up excited state, and then further excited states. But when you're trying to use just the qubit model, you have to somehow restrict them into just 2 states, the ground level and then one higher state. And today they're trying to do it using temperature control to keep them close to 0 Kelvin. So that becomes way more expensive because you have to somehow freeze them into specific states and then keep them in that state. But here with a continuous variable model, this thing here you see that's X8 from Xanadu. And we believe that this model is so much closer to realizing mass production because it can operate at room temperature and is compatible to the fiber optical communications network. So we're going to talk about that more. And that's the technology that quantum AI is basing its technology on. So with a quantum computing stack, I'm sorry. Okay, so let's do this from the beginning. I have to click on this. Okay, I'm here. Then I have to go back. Yeah, with the quantum computing stack, when people say quantum computing, they just kind of think about just like hardware or they talk about algorithm. But I think like James was talking about how all the applications we're using today that are so amazing could never be here without semiconductor revolution that came about via Intel by those treacherous eight. Those amazing people. The same idea, when you say quantum computing, people tend to stick with one way or another, but we have to kind of look at it as a full stack of us having devices. But then on top of that, we need control engineering. And then on that, we need compilers and like software on top of that. And then we actually have to have algorithms which solve actual problems. And right now, quantum AI is focusing on quantum algorithms based on the photonic chips that Xanadu made. And then there was quantum computing. In terms of quantum memory, we need to store quantum information for complex computations. Like if you do some kind of matrix multiplication, you're going to use it right away, but you have to store it even for temporarily. So the more complex computations you carry out, the more memory space you need. So this is kind of like an example of using quantum memory right next to the processor, and then they have to bus the information around. Or it can be used for quantum communications, as I mentioned, with repeaters, when the distance between two devices between which the information has to flow through, the longer the distance, the higher the possibility of the signal losing its integrity. So you have to boost it up by using repeaters, by boosting the signals and storing it and reusing it, that kind of thing. So quantum memory is really, really important as well. And as I mentioned, quantum transducers are devices that make disparate signals come to make them compatible to each other to be able to share their information. And then quantum sensing, sensing devices we have. So if we can use quantum states for sensing, that would be fabulous. And this is actually outside of quantum computing. This is the area where most of research is done. The application of quantum sensing in terms of industries would be, of course, military and defense, more than anything, healthcare, and then automotive and oil and gas. And this is kind of like an example of different areas of quantum sensing being used in biomedical industry, and especially for healthcare, it's going to have a huge implication. So then looking at all this, I use the term continuous variable, but that idea is actually analog, putting together Xanadu's photonic chips and the idea of using higher dimensional computational space. I believe that the future of quantum computing is going to be photonic analog. And the advantages of photonic analog quantum computing are many. Number one, it's compatible with the existing communications infrastructure, and it operates at room temperature, and that makes it so much cheaper to mass produce. And higher dimensional computational space. It's easy to network and multiplex with photons. You can use just fiber optics, optical fibers, just to connect. And they can be mounted on smartphones, laptops, and edge devices because you do not need any extra devices to keep the control, to control the temperature. So in conclusion, with 40 years of history, quantum computing research has come a long way, but still it's still at its infancy compared to where it can be. Yes, algorithm and hardware have to go hand in hand. Analog quantum computing offers higher dimensional computational space. Hence, you can compactify more information. And with fewer computations, you can produce way more. With photonic quantum computing, you can have more cost-effective solutions because you don't have to control the temperature. And however it is, quantum future is arriving. So with that, let's be ready for the quantum future, and thank you very much.
Any questions? Anybody has raised your hand? Right here.
Thank you very much for the presentation. Can you tell if this multidimensional computing is similar to what D-Wave is doing? Can we do like high parametric optimization problems?
Yeah, what D-Wave is doing is completely different. So they use quantum annealing. But I think about that, Imran, do you have something to say? Like,
quantum annealer is solving a big giant matrix. So basically you have just one unitary big giant matrix with all these inputs coming in and there's just one output. So that's quantum annealing. So which is different from gate-based quantum computing where you can think of adding different gates to build, let's say, something like a Shor's algorithm or solving a Grover algorithm kind of approach. So that's what D-Wave does with their basically hardware, is do annealing, but not gate-based quantum computing. Does that answer your question? First of all, I want to make sure.
Yeah, not exactly. So I'm asking, can we solve large-scale optimization problems with the gated quantum compute?
I think so, yes.
Can we use the same techniques that Chloe was talking about right now? Well, with the photonic-based?
With any modality. But now you talk about a loop where you basically have to do a sort of a measurement, where it's a computation, measurement, and sort of a feedback loop in there.
Is it feasible today to do so?
Not so, because the hardware is not there yet. We're talking about hardware which has tens, maybe hundreds of qubits. For running some of these optimization algorithms, which is kind of a low bar. We're talking about maybe a few thousand qubits. Maybe we can start doing some useful optimization or Hamiltonian simulation or measurement. But now if you want to run the more textbook-based quantum algorithm, let's say the Shor algorithm or Grover algorithm, for that you need millions of qubits, and no modality right now has that kind of hardware with that kind of number of qubit counts.
Okay, so not getting it. So how is it different from, okay, can it solve the same problems that D-Wave can, well, at least they claim to solve, like quadratic optimization problems?
No.
It cannot. Okay. Interesting. Thank you.
So why don't we chat offline? Because I think the matrix is a bit confusing right now. Because the thing is, there is promise and then there's potential, but then there's reality. The ground reality is the hardware right now is not there yet. So what people are doing is with the machines we have, can we do something else? And that something else part is what's growing right now, is being talked about. Some of it has to do with, you know, what you sort of talked about, or optimization problems, Hamiltonian simulations, things like that. Those are the low bars where the error rates required for the modality is not that large. But like the classic optimization, like the classic problems for quantum computing that you talk about in a quantum textbook, where you get exponential speed up, those are requiring much more sophisticated machines. They don't fall in the exact camp that you're talking about. Those are the classic example, such as the Shor's algorithm, which would be able to break encryption and things like that.
Okay, Thank
Okay.
you. Thank you.
All right. Maybe let's
Thank
chat
you.
afterwards.
That's close. Yeah.
So in terms of the photonic analog systems that you're looking at, so my understanding was most of the attention has been on both the error correction quantum computing, where like IBM and similar, versus annealing like D-Wave. Is the photonic analog one, is it programmable in a similar way as the error correction ones? Like,
Yes, Xanadu is actually becoming the place to go for quantum software because they integrated like Google's Circ and TensorFlow Q and IBM's Qiskit and pretty much a lot of other places. So that was really smart from their part, but they're kind of abandoning the photonic analog quantum computing that they originally developed. But they have a library called Strawberry Fields for building quantum circuits, and then Penny Lane for wrapping it for quantum machine learning, all Python based. So we're using theirs to build quantum neural networks and quantum transformers. And that's how we're going to build quantum large language models.
and just to follow that up, are there any additional restrictions that that their systems have compared to a more classical quantum computing system?
Yes. So when I said error correction, like, when I was talking about using elementary particles. So yeah, Imran was talking about maybe billions or millions, let's do 1 million. Let's say when we need 1 million qubits, like quantum bits, to solve any practical problems. Imagine 1 million elementary particles, and each one is forced to stay in only 2 states. So controlling all of that is really, really hard. And that's what they keep talking about, writing papers, how to error correct better. In the meantime, with Xanadu's system, it's programmable, as I mentioned, with Strawberry Fields and Penny Lane. And photons are much more robust to noise, and they don't have decoherence problem, but they have a different type of problem for control, what have you. It's not error-free, but they have a very specific algorithm, quantum neural networks, that they developed that works in simulation. By the way, all of the quantum computing that we are talking about, none of that is on actual devices. These are all on simulators, like classical computers. But yeah, so I think photonic has way brighter future than you say classical quantum computing, digital quantum computing. But without all the research that's been coming all the way to today, we wouldn't know what we know today, right?
Any other question?
Has anybody been able to demonstrate at a practical level room temperature quantum computing yet? Or is it still in simulation mode?
Oh, no. Xanadu makes their chip available from 15 to 21 or something. So this military time. So they make it available maybe 7 hours a day or something, Monday through Thursday. This is the same state that any other quantum computers have, that nobody has stable and viable enough chip that somebody can use for days or weeks to do anything. So Xanadu is in the exact same boat as any other quantum computing companies, but they do it at room temperature.
So is then the real challenge first, when you look at the technology stack, that you have to have a stable hardware environment before you can begin to apply the application layers? I mean, it's like going back to how we built von Neumann architecture on the whole bit, right?
Yes.
Am I oversimplifying?
No, exactly true. But still, the quantum computing researchers, they know that quantum era is still far out. But then we still need algorithms, right? So at Google, they have X Prize and they have X Prize Quantum competition happening. So we signed up for that actually. So what they're one of many areas, one of the is to develop new algorithms based on quantum principles so that when the actual hardware comes, we can use this.
Since I'm not smart like you guys, so it's like, okay, so first I've got to be able to demonstrate through a synthetic set of experiments, a proof of concept around not actually doing quantum computing, but I could simulate it. Then is the next step, then I go, okay, I take that I can prove this, through simulation and through some algorithms. Then you go back to the hardware guys and go, look, guys, this is how it works. You need to build something that can do that. Is that how it works?
So that's
what I
how
struggle. I
yeah.
struggle with the technology stack because I don't know. And that's why I'm asking.
Yeah, that's how they've been doing, because originally with Rigetti and IBM, they showed that these physical devices are actually possible. Then, especially with Rigetti, they got a lot of funding, but then like we have hardware, so what now? And then a few days later, like hardware alone doesn't do anything. We actually need some software and algorithm. So that's how that algorithm field got really, really developed. So then when the problems with hardware was way larger than we thought, it's taking way longer to solve, then people go, okay, while they're doing that, provided that all this error correction models, they all work, still, what are we going to use them for? So algorithm research has been going on for a while. So I think, yeah, it's
Is this like classic error correction? I got bad data. I got bad series of qubits in data in memory, right? Is it like that?
Yeah. So you basically
Okay.
have redundancy.
Okay.
Yeah,
I get it.
Actually, let me just add to there's a lot of questions coming on the application. So let me just spoiler alert. So as far as practical quantum computing on actual hardware, right now, quantum computers today are only doing what's called QoE problems. So that's that. Now, you asked about quantum simulations. We can use GPUs, and I think that's been NVIDIA's pitch to use their GPUs to do quantum simulation. But I think they hit a limit with their compute power somewhere in the vicinity of 40 to 50 qubits. Is after that, it gets too complicated to get. So, or it's just the computation is just too complex to do a quantum simulation above 50 qubits. So that's why a lot of quantum computing modalities are trying to get to above that 40 qubit, 50 qubit mark. So that now they can build a hardware with reliable 50 error corrected qubits. And now a new game begins.
Actually, that reminds me, maybe it's going too deep, but with photonic quantum computing that Xanadu developed, what happens is that with the qubit models, you have computational qubits, and then you have readout qubits that are separate. So to carry the computation, let's say if you have 10 qubits, now you need like 4 or 6 additional qubits just for readout. But it doesn't happen in photonic. It's all in same chip all together. So it's much more natural. So once again, that's why I'm just a firm believer in photonic quantum computing.
Question, Sophia. Thank you for your presentation. So no doubt quantum computing is coming. It has a lot of benefits. Has anyone looked into the power consumption that quantum computing running LLM at the same time requires?
Yes. So for quantum AIs, quantum neural networks, and quantum large language, like quantum transformers, you have way fewer number of parameters to train, and then it converges way faster. So you have quantum circuits, so you do forward pass, and then you are updating the parameters using back propagation on classical computer. But then when you're doing that classical computer, the number of parameters that you have to update becomes so much smaller.
Say that again.
I see. Okay.
So So with quantum neural networks or any kind of quantum machine learning algorithms, all the models that are out there, you have parameters that you're training to update. That training is done on classical computers, but then those parameters are the parameters to control gates. Yes, yes. So when you have way fewer number of parameters to train, of course, computational resource become reduced. But forward pass in simulation, you still need more. So that's what we want to solve.
Yeah, I think I actually had this question. So if you're not solving minimization problems, how do you actually do training and backpropagation? But you answered that you actually are not training, you're not supposed to be training a neural network with quantum computer, right? So what is the actual benefit then of using?
Oh, training is using quantum circuit.
So you are using quantum circuit to do the training.
And then backpropagation is using classical computer.
Okay, so
Yes,
can I
yes.
then formulate the question? So if you're not solving the minimization problem, how are you actually are training the parameters? Because that's an optimization or minimization problem, right?
Oh, so then optimization is done on classical computer.
Okay.
So for example, we have to do more, we are open sourcing our quantum transformer, but from our initial experiment with like Portuguese to English translation, like when you have like 6 stacks of transformer with classical, you would need like 33,000 parameters. In quantum, with the exact same architecture, we only needed like 228.
Okay, thank you.
One last request. Can you, Sophie, can you and Arjun, I would love to do this with you, as a co-production, a Quantum 101 online educational, because, I know von Neumann architecture but the quantum is like, I have friends that understand more than me, but I would love to get basic education around quantum.
Yes, Alex, she studied physics from Yale, and she's going.
He's really smart, by the way.
Yes. So she's gonna continue her studies in physics in Denmark.
Okay.
So we are trying to come up with some kind of curriculum for quantum and quantum neural networks on Coursera, and for university course, like 10-week course. So we want to start small and we want to build up. We have some other like CS students from Stanford that we can work together with her. But right now, I have one junior developer who's actually putting a product together. And then when I have 10 brilliant ideas that Arjun is feeding me, implementation wise, I only have 24 hours.
Yeah, I know. Then let's talk after this, because I'd love to give you guys a forum through the Intel Alumni Network to do kind of this continuous education. We do it around generative AI now. We've done, generative AI 101, 102, and 201. We're going to do 301 in October, but I would love to start a series on quantum. Right.
That'd be awesome.
And we could involve, because I'm also connected with the Microsoft Alumni Network, and they got 60,000 members worldwide. I mean, this could be a really interesting series, of nerd patrol discussion about, the evolution of computing, right? Because that's what you're talking about. You're talking about a changing in the compute model, and it has huge implications if we can pull it off.
Coding.
Yes, well, yeah, I mean, it's the full technology stack, right? So we need to talk, because we used to have a classic von Neumann architecture computing stack. Now we're talking about something that is fundamentally different. And I really don't think even people in technology, and me included, I don't really understand it. I genuinely don't, right? And I really would like to learn more. So that's the input. And as entrepreneurs, being seen as thought leaders in any new category, I can tell you, is I'm more business than technical. That is that's where you need to be, in my opinion. So.
Yes, so Imran has been working for a quantum computing company for 5 years. And yeah, but he's in software engineering. So with your idea, we should be able to bring some people together. But I think, yes, a new kind of quantum is emerging. Then we can all join together to open a new quantum future.
Let's make this the Intel alumni event for November.
Okay.
Because I have a slot in November, Arjun. I got a slot. We produce a thought leadership program a month. We'd love to have you do this. This is a lot of fun.
All right, fabulous. We still have some food and drinks. And
I had a quick question on the actual what's on the Xanadu chip. Assuming there's a photon source, waveguides, splitters, but could you describe, what's on that chip, and if you know how it's manufactured, I'd be curious.
yes, so Xanadu has a lot of patents. We want to either license from them or we want to form a coalition to improve upon that as an AI accelerator. Once we have quantum large language models that actually work, that we can work together with either NVIDIA or Mistral, that kind of thing. So then with the device, they actually made it when they had less than 5 million raised. They actually came up with the prototype. It's because they're using like laser technology and optical instruments. They're like off the shelf, they say, very cheap. So first you have the source of light, which is classical from laser. And all the quantum optics people know you go through the process of squeezing. The squeezing is like, I forgot which position of momentum. You squeeze either of, I think it's the position, and the momentum gets spread out. Then it becomes that complex coefficient of a lot of bases because you can't really know it here. So now it's probably distribution, and then it becomes quantum. And then with that, they use beam splitters, rotation, squeezing, displacement gates, and Kerr gates. These, like, I don't know anything about this, but these seem to be just everyday devices, effects for quantum optics people. And then later they do quantum photon detectors. So per waveguide, they see how many photons are observed in that. So that's the measurement process. So I think they have up to 8 waveguides that they're using. They call it quantum modes. So increasing the number of modes would be beneficial, and tightening up these different components to higher precision or what have you, that would be very good. So then, computational resources wise, it's photons, plentiful.
Thank you.
Okay, thanks, guys.
Thank you. Thank you so very much.
So we have food outside.